So I'll try to not use up the full 2 lectures on Thursday. So hopefully, without a break, hopefully we can end by 5:50. Okay, 5:50. So originally it goes up to 6:20, right? So I'll try to end, well, without a break it goes to 6:10. So I'll try to end 20 minutes earlier. Okay. All right. Okay. So yesterday we started to talk about a few basic transformations of the independent variable. Okay. The first kind is time shift, right, which refers to shifting the signal in time either to the right or to the left of the origin. Okay. So a time shift can be represented as, the original signal x of n minus this time shift n naught. Okay. So if you have x of n minus n naught, with n naught being positive, then you're moving this signal to the right by n naught. Okay? And the way to justify this is because, if you observe the value at time 0 of the original signal, you will see that this value will then occur instead at time n naught in this time-shifted version. Okay? Because if you plug n naught into n here, you will get exactly x of 0. All right, so this is sort of a simple way to check if you have done the time shift correctly. Okay? Now the second kind is time reversal. Time reversal simply refers to the reflection of the signal about the origin. Okay? And mathematically, right, if the original signal is x of n, then the time reversal is expressed as x of minus n. Right? So this is a reflection because the signal that you observe originally at time n naught, right, this signal that you observe originally at n naught, after time reversal, now appears at time minus n naught. Okay? And you can also double check this, right? If you substitute minus n naught into n here, you will see that this value is indeed x of n naught. Okay? Right? So if this is x of n naught, then at time minus n naught, you will also observe x of n naught. Okay? At time minus n naught of the time reversal, you will also observe the same signal. Okay? And this is the same for continuous time signals as well. Right? Now, the third kind is time scaling. Right? So suppose originally your signal is x of t, then if you scale the independent variable by some factor that is greater than 1, then you're effectively compressing the signal, right? And the reason for that is because suppose you're looking originally at the value occurring at time a, which would be x of a. Now this value x of a occurs earlier at time a over 2, okay? And you can double check this because if you substitute a over 2 inside here, x of a is exactly the value that you get, okay? So if you multiply the time variable by some factor that's greater than 1, then this is like fast forwarding your signal. Okay? Now, if you instead multiply t by a factor that is less than 1, then you're actually, stretching the signal, or in other words, sort of slowing down. Playing the audio or video in slow motion. Okay, so it extends over a longer period of time. Okay, so more generally, you can represent these 3 types of basic transformations in a simple form of x of alpha t plus beta, where beta represents the time shift, and alpha right, depending on whether it's greater than 1 or less than 1, either compresses or stretches the signal. And depending on whether alpha is greater than 0 or less than 0, right, you may have a time reversal or not. Okay? All right, so last time yesterday we were in the middle of this example. So we were looking at this signal x of t, right? The signal x of t here. And we want to see what it looks like after, these different transformations, okay? So we completed the first two, right? So if you first look at x of t plus 1, then x of t plus 1, right, is just a time-shifted version of x of t. And this is shifting the signal to the left by 1, okay? So you can double check this because, the value you originally observed at time 0 now should occur at time minus 1, because if you substitute minus 1 inside here, you will get exactly x of 0, okay? So this x of 0 here, after a time shift, okay, now occurs at minus 1. Okay. Now the second example is x of minus t plus 1. Okay, x of minus t plus 1. Now if you view x of t plus 1 as a signal y of t, then x of minus t plus 1 is just a time reversal of this signal. Okay? So if x of t plus 1 looks like this, then x of minus t plus 1 is just this flipped around about the origin. Okay? All right. So let's continue with the third example. So the third example is the case where we multiply the independent variable by 3/2. Okay? So this is a time scaling, right? Now, is this a compression, or is this compressing the signal or stretching the signal? Compressing, right? So because we're multiplying by a factor greater than 1, so we are somewhat fast-forwarding the signal, right? Making it occur over a shorter duration of time compared to the original signal, okay? All right, so this signal would look something like this. Okay. So suppose that, okay. So this signal should take on the same shape as the original signal. It's just that it should be, compressed, right? It should be squeezed towards the origin, okay? But by how much, right? So we can sort of look at particular points here. So for this point, let's say x of 2, right? In order to get the value x of 2, t must be how much? Right. In order to get 2, t must be 4/3, right? Right? So this means that in this compressed signal, this point should now occur at the point t equal to 4/3. Okay? So maybe I can draw this closer. Okay, so that it actually looks compressed. Okay? Right, so this point should now occur at this point, and everything else should be scaled accordingly, right? So the 1 should now occur at 2 over 3. So our signal should look like this. Okay. Right. So the signal here, x1 now occurs here, which is also x1, right? And the signal x of 2 here now occurs at time 4 over 3. Okay? So the shape is the same. It's just squeezed so that it's fit into a smaller duration of time. Okay? So for the fourth example, we have x of 3 over 2t plus 1. Okay. Now you can look at this in two different ways, right? You can view this as, a time shift of this signal, okay? Or you can view this as a compressed version of this signal, okay? Or in particular, y of t, okay? So the second approach is a little bit easier, right? Because if you view this as a compressed version of x of t plus 1, then you simply take this signal and compress it, okay, to the point 2 over 3. All right? So this is one way to look at it, right, as a compressed version of x of t plus 1. Okay. Now, another way to look at it is as a time-shifted version of this, okay? But treating this as a time-shifted version of this is a little bit trickier because this signal is not this signal shifted by 1, okay? So in order to compute the correct time shift, you should take into consideration the scaling that you have done to the independent variable, okay? So now, to get the correct scaling time shift, you should instead write this signal as x of 3 over 2 t plus 2 over 3, okay? And the reason is because if you view the above signal as some signal z of t, right? Then the signal you have here is actually z of t plus 2 over 3. Okay? So you're actually replacing t with t plus 2 over 3 in order to get this, okay? So if you want to view this as a time shift of this, right, you're actually shifting this to the left by 2 over 3, okay? So doing it this way is also okay. It's just a little bit trickier, okay? Okay. So because the first approach is easier, right, therefore the textbook suggests the first approach as the rule of thumb. Okay? So the rule of thumb suggested by the textbook of obtaining x of alpha t plus beta is to first shift by minus beta before you scale by alpha. Okay? Because this is less confusing. Right. So any questions? Any questions? Okay. 有没有搞不清楚怎么样得到这张图的？ Okay. So this shouldn't be difficult. You just have to be, careful in each step that you do. Okay. Just double check. Just do a simple double checking in every step that you do. Okay. Right. So an easy way to double check, right, is just to plug in the time variables and to see if it gets you the value you want, right? So if you plug in 2/3 inside here, you get 1 plus 1, which is x of 2, and indeed, this point is x of 2, right? Just do this simple checking, and you'll know if you have done it correctly. Okay. Now, a class of signals that we're going to talk about a lot, especially in chapter 3, is the class of so-called periodic signals, okay? So intuitively, what are periodic signals? Periodic signals are signals that repeat itself at integer multiples of a certain time period, of a certain time, which we call its period, okay? So mathematically, right, we say that x of t is a periodic signal if there exists some time capital T greater than 0 such that x of t is equal to x of t plus capital T for all t. Okay? So this for all t is essential. Okay? So no matter which point you're looking at, right? If you time shift by capital T, you should observe the same value. Okay? So this is the property of a periodic signal. Okay? So if x of t, if there indeed exists this capital T such that x of t is equal to x of t plus capital T for all t, then we say that x of t is periodic with the period capital T. Okay? And if you cannot find such a capital T, then you say that this signal is aperiodic. Okay? Right. So in this case, we say that it's periodic with period T. Okay? Otherwise, it's aperiodic. Okay? Now, these are some typical examples that you may observe in practice. Right, so for example, if you're observing the voltage across a capacitor in this LC circuit, right, then you will see an oscillation of the, of the voltage as the capacitor discharges and charges, right, as this energy goes, between the capacitor and the inductor. Okay? Or if you're looking at the location of a ball on a spring, right, then if you view the signal as the location of this ball as time evolves, then you will also see a periodic signal, assuming that there's no, friction friction causing it to slow down. Okay. Right. So these examples give you periodic signals that look like a sinusoid, right? But certainly periodic signals do not necessarily have to be sinusoids, right? You can have, periodic square signals, periodic triangular signals, and so on. If you say that a signal is periodic with period capital T, okay, then it must also be periodic with period 2t, 3t, 4t, or any integer multiple of capital T, right? And this is because, right, for a signal to be periodic with period capital T, x of t must be equal to x of t plus capital T for all t. So if you look at a t that is equal to x of t plus capital T, right? If you plug in t plus capital T inside here, then it should be equal to x of t plus 2t. Right? So similarly, if you plug in x of t plus 2t on the left-hand side, then it should be equal to x of t plus 3t, and so on and so forth. Okay? So this is saying that if x of t is periodic with period capital T, then it must also be equal to x of t plus 2t for all t, and equal to x of t plus 3 capital T for all t, and so on and so forth. Okay? So if a signal is periodic with period capital T, it is also periodic with any integer multiple of capital T.